Good afternoon. My name is Larry Connor. I'm with Ryder Scott Company. And today I would like to present the process of utilizing the water-oil ratio versus cumulative oil methodology in PHDwin version 3 to estimate reserves. First, a little bit about the agenda for the day. We're going to start off with general references for immiscible displacement and a few definitions. We'll look at the fuel level analysis issues, the water-oil ratio versus cumulative oil analysis. We'll talk about general requirements, issues. We'll look at some example extrapolations with real data. And then we'll move to examples where I will demonstrate utilizing version 3 and the water-oil ratio versus cumulative oil analysis. We'll take a look at a water flood example, and then we'll move to a high water cut single well. Now, this high water cut single well is new in version 3. I think it's a very big improvement over version 2, and I'm sure you're going to enjoy that. Listed here are several general references that I and others have found very useful in analyzing water floods. In addition, later in the presentation, you will see a reference to an SPE paper that specifically discusses water-oil ratio versus cumulative oil projections. The definitions. As you can see, there are several definitions presented here for you. First is the fractional flow of oil rate divided by oil plus water. The fractional flow of water, which is the water rate divided by oil plus water. And of course, the one for water-oil ratio is the water rate divided by the oil rate. I'd like to point out that if you take a look at the oil fractional flow and you divide the right-hand side by oil, you will end up with 1 over water-oil ratio plus 1. And if you look at the equation for water-oil ratio plus 1, you'll see that it is the inverse for the fractional flow of oil. Well, I'm sure that you're all familiar with these definitions shown, but I wanted to show them here so that you clarify them for in your future reference. You can do some quick math, and you can see that a water-oil ratio of 49 is equal to 98% water cut. And a water-oil ratio of 19 is equal to a 95% water cut. And a water-oil ratio of 4 is equal to an 80% water cut. You may want to keep some of these in mind when you are going through the presentation today, because we're going to discuss about what kind of water-oil ratio or water cut to cut off your projections. Well, there are several hot buttons when we talk about the water-oil ratio method and why they're not recommended to perform field decline analysis by groups as opposed by well. Some of these reasons may be well activity like workovers and other stimulations could mask the real decline of the reservoir. For multi-layer reservoirs, performing a full field decline would aggregate the behavior of several layers in a group plot, with the risk of estimating an optimistic hyperbolic decline factor in the analysis. Drilling activity can mask the response to water flood. Incremental response from ongoing water flood or EOR processes could mask the underlying field decline. So all of these combine into some issues that you might encounter while analyzing WOR versus decline curve analysis. Well, let's talk about some of the hot buttons. There have been instances when Ryder Scott has recommended field or group decline analysis for evaluation in certification and reservoir studies. In those cases, it's has often been by using the water-oil ratio cumulative oil plots. Writer Scott recommends the use of the water-oil ratio cumulative oil plot or other cumulative oil methods when the conditions are appropriate to do so. We recommend the use of this method on a well-by-well basis in order to have a better control of the reservoir variables. The accuracy of this method for group or field plots in the same way as a traditional decline curve analysis when you combine several wells into a production stream. Well, what are the requirements for utilizing this analysis? The general requirements for the use of the water-oil ratio cumulative oil method should be for water drive or water flood operations if the reservoir fill-up has been achieved, reservoir pressure is constant, steady state conditions with stabilized rates, breakthrough should already be achieved. And I quote SPE paper 20064, and it gives some general guidance on this topic. It's easier to evaluate when a single reservoir is producing. Producing rate is subject to variations of water volumes injected or influx rates. Obviously, operating conditions have an impact on a water flood performance. Injection rate and pressures have a direct impact on aerial and volumetric sweep efficiency and will impact the water-oil ratio versus cumulative oil analysis. This can be especially true if there are multiple reservoirs under water flood or at various stages of fill-up or depletion. Log water-oil ratio versus NP plot. The SPE paper 77569 states the log linear relationship of a water-oil ratio and oil recovery allows for the extrapolation of observed straight line to any desired water cut as a mechanism for determining corresponding oil recovery. This paper points out that the log linear relationship of water-oil ratio and oil recovery are essentially empirical and requires simplifying assumptions, such as the mobility ratio is equal to 1, and that the plot of log KRW, KRO versus the saturation of oil is linear. This approach is only used when a straight line can approximate the function of water-oil ratio, and therefore the data must present a straight line before the methodology can be used. Unfortunately, in most cases, this method is not applicable in the early stages of a water flood. The general rule of thumb is that the log water-oil ratio versus NP plots cannot be used for less than a water-oil ratio equal to 1 or a 50% water cut. Caution should be used since misuse of this empirical technique can yield substantial errors in the extrapolation of recoverable reserves. Well, let's talk a little bit about the method itself. On top of dealing with the noise from multi-layers, we have to deal with the noise from workovers, from different wells that may affect a pattern recovery, recompletions, oil responses at different times from different wells, and any operational changes that are involved inside a group or a pattern. The plots, water-oil ratio versus cumulative oil, can be helpful at a group or pattern level for injection surveillance. And you can observe changes in the slope of the plot, and that can be very insightful as to what may be going on in a pattern or a group. They can be used for oil reserves estimations when the conditions are appropriate to do so. Well, let's take a look at a real life example. Now, you can see in this particular case, the fault block to the north may in fact be separated from those fault blocks to the south. And they may not be in hydraulic communication. Therefore, it would be inappropriate to include those wells in the lower half of this reservoir with the wells that may be in the northern half. So it's going to be very important for you to analyze which of your wells may be in communication and which wells may not. Therefore, paying attention to the wells that are in your group is going to be very important. When using the water oil ratio versus cumulative technique, it is important to select the area that is in the hydraulic pressure communication. If your area has sealing faults, or select the wells that represent the area studied. Well, injection patterns. It's common practice in the industry to do it by injection patterns, if it is a pattern water flood. The downside of this method is that the producer production has to be allocated geometrically or depending upon the actual trends on the pattern itself. Some companies and a lot of our clients have programs for injection profiling to keep track of these allocation numbers. In the example shown, the oil production in a 5-spot is allocated using 1/4 of each producer to the pattern in question. Well, let's take a look at some real life examples. In the case that you see in front of you is a situation where there are apparently several breakthroughs where you see the water oil ratio increasing and then decreasing. This is an indication that there may be an oil bank that's being built. You can see that it occurs several times. Again here, and again here, where the water oil ratio increases and then declines, and perhaps a oil bank is being built. And then you see that the linear extrapolation of the trend as the reservoir becomes stable. As previously described, the water oil ratio versus cumulative oil analysis is only good when the trend has established this log linear straight line trend. In this example, the trend begins at approximately a water oil ratio of 4 to 5, and that represents about an 80% water cut. And we recommend that we wait until a clear breakthrough in the reservoir to forecast the plot. The second recommendation is that you be cautious of projecting the same or a similar trend as the one prior to a breakthrough, especially if we know that there are multi-layer reservoirs. And again, you can see here that there may have been a breakthrough. Maybe a second zone had a breakthrough, and then maybe even a third zone had a breakthrough. And then there might even be a fourth breakthrough before the reservoir establishes the final trend. Specifically, I'd like for you to take a look at the parallel line, where if the extrapolation was moved to that parallel line, you might significantly over forecast the ultimate recovery from this reservoir. In this example, one of the reservoirs has actually reached a breakthrough, causing a change in the slope in the water oil ratio versus cum oil. The third recommendation, consider fitting the last trend. Just like in conventional decline curve analysis, this last trend may be the most important and the one that deserves your attention. Well, utilizing PHDwin water flood analysis, let's go over a couple of the issues. There are two defined relationships when we talk about water-oil ratio cumulative oil analysis. The first relationship is total fluid as a function of time. It is for a water flood analysis, we will utilize the well count multiplied by the fluid per well to derive the total fluids. In the case of using the high water cut single well analysis, we'll use the total fluids and utilize the direct projection of the total fluids. Well, given any month, we can easily calculate the total fluids. It is a direct function of time and a result of a projection of total fluids. If we know the total fluids and the water-oil ratio, we can easily calculate the oil. But wait, the water-oil ratio is a function of cumulative oil, not time. And therefore, calculating the water-oil ratio at any given month requires a convergence calculation. First, you guess at the month's water-oil ratio based on history. You multiply the known total fluids at this time step and calculate the oil cumulative of the new month. In addition, at each time step, the water is calculated. We will then check the estimated water-oil ratio against the water-oil ratio versus cumulative oil relationship that we have by our forecast, and they're likely not going to match. So a better guess is required, and the process is repeated until the water-oil ratio in the month is the same as the water-oil ratio projected in the input. This process is repeated for each time step. Well, now we need to discuss about the ways to create a reliable forecast. The first thing we're going to do is we're going to project the water-oil ratio versus cumulative oil. We're going to pay specific attention to the latest trends and the most recent data. We're going to project the total wells on a rate time. And if it's a declining trend in the total well count, the engineer needs to make a judgment decision that will that decline trend continue in the future, or will it remain flat from this point forward? It will make a difference on the ultimate recovery and the projection of the oil and the water. Next, we'll project the total fluid per well on a rate time basis. Generally, I hold this flat, assuming that the constraints will be constant, the injection will be constant, and operations will be constant. And then we were going to take a look at the water flood example. And I'll start up PHDwin in a few minutes, and then we'll go through this example. But the following steps are those that are required inside PHDwin. We're going to create a group case, and it'll be a projection unit. We'll add the children cases to that water flood unit case, and we'll compile. We'll set the phase configuration to water flood. We'll add a log rate cumulative oil graph. We'll add the water-oil ratio versus cumulative oil, and then we'll forecast it. We'll add the fluids per well and total wells to the rate time plot. And we'll forecast the well count. We'll forecast the total fluids per well. We'll repeat this process for the high water cut example, except that the phase configuration will be set to high water cut, and instead of fluids per well and total wells, we will add the forecast total fluids, since one well count is assumed. All right. And at this point, what we'll do is we'll stop and begin the PHDwin version 3 analysis.
Well, here we are. We've opened up PHDwin version 3. And this is build 3.1.10. This is the new version of PHDwin. As our demonstration today, we're going to start off with the water flood example. And so we're going to create a unit case of the Hilcorp properties. So the first thing we want to do is go to the Home ribbon, Add Import, Economic Group Case, Projection Unit. And that's going to add a new case. You can see it added the new case, but it came in as red. So that indicates that it's coming in as a gas well. We're going to want to make sure that we get that corrected before we start our projections. Well, we want to grab the Hilcorp cases, drag and drop on the case settings. You'll notice that 121 cases came in, and that matches the total Hilcorp cases. So we have all of the wells included. And we want to compile. Well, it's finished compiling. Let's go back up to the General Information tab, and let's give it a case name. Let's call it the Endicott water flood. And you'll notice that the major phase is gas, and as I said, we want to make sure that we change that to oil. All right, that's done. The next thing we want to do is go to the Forecast ribbon, and we want to change the phase configuration to that of a water flood. And yes, we want to save. All right, notice it's green, it's an oil well, and it's in the water flood phase configuration. Well, there's a couple of things I'd like to do for housekeeping before we get started making our projections. The first of which, let's go to the database settings, products configuration, and you can see that we're standing on the water flood. You'll notice that there's no gas. If you intend to include gas in your economic analysis, you need to add gas to this configured products list. So we need to go into the edit mode. We're now in the edit mode, and I'm going to grab gas, and I'm going to add gas to the configured products. Notice it comes in scheduled in time. While we're here, let's check the high water cut case. And again, you can see that the default configuration does not include gas. If you want to include gas in your economic analysis, you need to add it as a configurable product. So we've done that. And now we're going to close. And we're going to edit the exit the edit mode. So now we're back. And you can see that I'm using the standard view. It's a view that I use quite a bit. But the one drawback is the individual plots are a little small. And so what I'm going to do now is I'm going to create a new view for the graphs. To do that, we'll come up, we'll select blank. Now we have an empty canvas which we can create a view of our graphs. Notice I'm going to drop the graph on the center box, and that will take the entire graph. And I'm going to grab the log rate versus cum, and I'm also going to drop it in the center box. And when I do that, it will create tabs at the top. And you can see that it's really easy to switch between these graphs. While we're here, I want to save this view, and I'm going to call it graphs. And I'm going to apply. Well, we're now ready to begin our forecasting. As you can see, this is the log rate versus cum oil, but there's no water-oil ratio on this plot. To add water-oil ratio, you double-click. You find the water-oil ratio, click, drag, and drop. You can apply and close. And then it applied it. Well, I'm going to pull it up so we can see it a little bit. And there it is. Remember in the presentation, I said that you should not utilize the water-oil ratio versus cum analysis unless the water-oil ratio is greater than 1. And clearly, we have water-oil ratio much greater than 1. Well, let's begin our analysis. So if I zoom in then on this part of the graph, you can see that this last portion of the water-oil ratio appears to be in a very nice, stable, linear trend. Let's utilize that portion of the graph and add a projection. To add a projection to the water-oil ratio, I click Add, and I want it to be log cum. When I do that, the beginning water-oil ratio starts out at 0. Well, I want to change that so that I can now have the handles and have it easily so that I can grab those handles and adjust my projection. Well, that looks pretty good. Let's drop it right there. Now notice that the final water-oil ratio is 57. Recall from our discussion earlier that a water-oil ratio of 49 represents 98% water cut. So let's go ahead and put that limiting water-oil ratio in at 49, and I'll change the unknown to cum final, and I'll put in 49 as the limiting water-oil ratio. So it will then truncate that projection, uses that same slope to 49. So we're now at a 98% water cut. Well, we're done with the water-oil ratio forecast. So let's go now to the rate time projection. And I want to pull that oil down a little bit so we can see it a little better. And I want to pull the water down so we can see that. That's good. But recall I said that we need to have the total well count and the fluid rate per well. Well, those are not on this graph, so we need to add them. Double click, pull it down, and we need total wells. Click, drag, and drop. And we need fluid per well. Click, drag, and drop. Apply and close. This is the well count, and the black line is the fluid rate per well. I like to start with the total well count, and we're going to make sure that there's no projection on there, so we have a clean projection. I'm going to add a projection. I'm going to hold it flat. Just like before, the year starts out at the report year, and I'm going to back it up 1 year just so we have some overlap. I'm going to change the starting rate from 50 wells to 51 wells. And I'm going to change the total projection time to 120 months or 10 years. And there's the resultant forecast. The next step and last step for the water flood analysis is to project the fluids rate per well. So I'm going to identify that. I'm going to add a projection, and I'm going to add it to be flat. Once again, the start year is the report year. I'm going to change that so I have some overlap. And I'm going to change the total rate to 120 months. And I'm going to adjust that fluid projection just slightly. And when I do so, you can see that we've got a very smooth projection in our oil. We have a very smooth projection in our water. Well, you can clearly see that there's a drop here, and you should be asking, well, what is that? Recall that what I said in the discussion, that the oil is a back-calculated number. And what's being plotted here is not an ARPS function, but it is the actual back-calculated monthly oil. And this drop represents a partial month in that last month. So that's why you have that drop. So in conclusion, what we've done is we forecasted the water-oil ratio versus the cum major, and we truncated that at 49 water-oil ratio, which is 98% water cut. We projected a flat well count, and we projected a flat total fluids per well. And the resultant was a very smooth projection in the oil and in the water. And at this point, we're done and ready to go to the economics. The next part of our demonstration is I want to demonstrate to you a high water cut phase configuration. This is new in version 3. This is a case where you have a single well, and we're going to make the same type of calculation on a single well that we did on a water flood case. The first thing we need to do is ensure that it is a oil well, and it is. Come to the configuration, and we want to select high water cut. So now we have the high water cut. And remember I said that the well count is assumed to be 1 in this phase configuration, but we do need to add the total fluids. And you can see it's not on the graph. So find total fluids, click, drag, and drop. Apply and close. I'll just get rid of that projection. Let's go to the log rate versus cum major. And you recall that we need the water-oil ratio versus the cum. It's not on this graph. So what we need to do is add it. Let's go to the water-oil ratio, click, drag, and drop, apply, and close. Remember that what I said in the demonstration or in the presentation was it needed to be greater than a water-oil ratio of 1. It is, and it looks like there may be a linear trend starting here. Well, let's make a projection on the water-oil ratio and see how it looks. I select water-oil ratio. I add a forecast, and I want log cum. And again, it selects the cumulative of 0. So I'm just going to change that to a number so I can grab my handles. and I'm going to project it out. Well, notice that my cum final WOR is 6.3, and this is a offshore field, and let's cut that back to a water oil ratio of 4 as our final ratio. Well, I want to make the cum as the unknown. I'll reset my curve, and I'll reset my final as 4. And I changed the truncated water oil ratio at 4, which is a 80% water cut. And I think we're ready to move to the rate time. So here we have the rate time, and I want to forecast total fluids. Identify total fluids as the active curve. You want to add a forecast, and I want it to be flat. I want there to be some overlap, so I'm going to change the year. And I want to change the projection to 120 months or 10 years. So you can see you have a really smooth projection in the oil and in the water. And like before, you've got that little bitty downturn, so it's almost a full month in this last month. Well, let's go take a look at something. Let's go back to home, and let's choose our standard view. And from here, I want to go to the monthly production. And notice I've got the display forecast selected. The actual historical is in gray, and the forecasted projection is in yellow. So you can see now that we have got oil in water projected. And that concludes the demonstration.
Well, thank you very much for this opportunity to present water oil ratio versus cumulative oil analysis utilizing PHDwin version 3. As you saw from this afternoon's demonstration, the high water cut analysis for a single well is a big improvement over version 2. And I think that it is going to make your workload a lot easier and a lot more straightforward. If you have any questions, you're welcome to contact me with the information that's shown on the screen. If I can be of assistance, allow me to help. Thank you very much. Have a good day.